Today I am here with the team WARR from the TUM University of Germany. Could you start by introducing yourselves?
I'm Yanis. I'm the leader of the project Nixus. That's the bi-liquid project. And I study mechanical engineering.
And I'm Moritz. I'm the team lead of the thrust chamber team inside of Project Nixus and study Airframe.
This year you are still working on a bi-liquid rocket engine. Are you always intending to use liquid oxygen?
Yes, we are actually this year at EuRoC going to fly exactly the same, and not exactly the same engine, but the same thrust chamber, the actual combustion chamber with the new improved additive manufactured injector, but the propellants will still be ethanol and oxygen.
Last year you've had quite a bit of issues with the fueling of the rocket. Have you been able to address some of those issues?
Most problems, I would say, were not with fueling of the pressurization. We had some problems with mechanical regulators freezing and not behaving to the correlations we previously determined. But we have since switched those mechanical regulators for electrical regulators based on a ball valve and servo. So they should be much more reliable in that way. And we have also made improvements to the quick disconnect, for example, for fueling.
Yeah, and don't forget also the feed system that we're going to apply this year is going to be much simpler. At least that's the intention of it. So that, it's less prone to failure.
So you will basically be flying the same engine, the same thrust chamber as last year, but you say you have changed the injector.
Yes, correct.
What have you changed in it?
Previously, our injectors were conventionally manufactured, and now we have one integral AM manufactured injector that allows us to adapt the geometry a bit better because we have more design freedom in AM, and we also were able to remove a lot of seals because we had a lot of places where we had to seal those mainly two injector compartments, so the ethanol and the oxygen. And by switching to one integral piece, we now only have two seals in the entire thrust chamber assembly, which should make the a lot more reliable. Not that we had any issues with that in the past, but it was obviously much more reliable. Plus, we saved over a kilogram in weight compared to the conventional manufactured version, which was the main driver to go with that.
If you remember well, you're with the shower head injector.
It's an impinger.
Impinging.
Yeah, a triplet, unlike impinger.
The thrust chamber is made of Inconel, if I remember well. The injector, is it always of Inconel or is it made of... You say you have simplified propellant supply for the rocket engine. What have you simplified and how?
Well, especially from an integration procedure, there were some challenges that we're facing. Right? The carbon fiber skins that we have, they're load bearing. So in the integration, it's a bit complicated to integrate the skins with the feed system if stuff has to go through the skins, right? Because of accessibility reasons. So this year we've adapted our structural connector concept a bit so that we can feed lines. So it allows us to have more flexibility in at what point we integrate what part of the feed system, to put it simply, right? And that way it saves us a lot of time, and there's much less potential for things to go wrong in integration.
And also, in the past, we had places where, for example, had multiple off-the-shelf adapters or T-pieces, for example, to connect different things together. And in some places, we have now combined them to like the custom manifold block, we could call it maybe, to also get rid of a lot of places where you could have leaks, for example, because the fitting was not tightened correctly, and also, again, to save weight and space.
Yeah, and then one more thing. We also flange a lot more of the valves right on the tank. So we have more interfaces with the tank rather than an intricate system that only has one interface with the tank.
Regarding the rest of the rocket, that is the Airframe and the Avionics, do you have something similar to last year or have you changed much in it?
Well, Airframe-wise, we have for sure reduced our mass, but the approach is the same, right? So still the load-bearing skins, still the same fin can design, just slightly adapted. One big change there is that the ethanol tank will hopefully be made out of carbon fiber. It's a development that we've kicked off about a year and a half ago now, more or less. And the idea there is, of course, that you can reduce the weight of the tank by switching from aluminum to carbon fiber. There's different, let's say, stages to it, and we're trying to build a Type 5 tank so that that means that the liner is carbon composite as well. There is no liner. Yeah. That was a big change this year. We'll see if the development will be flight worthy in time. We're on a good path, but there's always, of course, things that can go wrong in such a experimental development. And I think the other part of the question was about the avionics. The flight computer will still be the same as last year, just because it's flight proven, which gives us a little bit of confidence there, right? Because we have so many other, let's say, developments that are a bit out there compared to what we did so far. So having a bit of certainty on that end helps us gain confidence in our safety concept for sure. There is an addition to it though. So with the electronic regulators that Moritz mentioned earlier that we're flying, we have an additional board that basically handles the control loop for the regulator, and that interfaces with the rest of the system through a separate board. And this year this will sort of be the first step towards this kind of approach where the avionics are more decentralized, right? Because so far we've always had the PFC, so the primary flight computer, in one spot in the rocket, and in the future we would like to spread it more throughout the rocket and then have it all interfaced through a bus system. So that's the first step towards.
Why would you like to spread the avionics around the rocket? Is it to simplify cabling?
Yeah, pretty much cabling and integration, right? So the advantage of a bus system, you can see it in cars, for example, is that if you have an integrated system where a lot of electronics are spread throughout the thing, right? So in that case, the thing is a rocket. If you had the computer only in one spot, you would have to route each and every cable that you need to go to a component through the entire rocket, right? And if we have a bus system, all we need is this bus system throughout the rocket, and we greatly reduce the amount of wires that we need to route, the space they take up, and hopefully also the weight.
Yeah, and it should allow for better pre-assembly of a segment, for example. So we could already here in Munich prepare a tank with the corresponding fluid segment, or the valves that need for that, the piping, plus the then avionics segment that goes in this assembly. And then the only thing we need to do in Portugal is screw them all together and connect the, in our case, CAN bus lines and the power lines. And then the rocket is basically integrated at the moment. You have to also prepare the segments here at home, but then you have to figure out how to get this huge wiring harness all the way through the rocket. And this just takes time in assembly integration that we would rather spend here in Munich.
Yes, of course. The EuRoC teams always have the goal of spending the least amount of time possible assembling the rocket. Clearly, the bigger the rocket is, the more complex that task becomes. Will the rocket be of similar size as last year?
Shorter, actually. Even though we have bigger propellant tanks, because we want to fly to a 9 this year, so much higher apogee, we were still able to reduce the length to 5 meters and 15 centimeters is the current best estimate.
Would you be the first team to fly 9 kilometers on liquid?
As far as I'm aware, yes, but we were not there from the very beginning, so maybe there's something we're missing.
Because I don't think I have seen liquids fly to 9 kilometers.
Well, it would be really cool to be first.
Also because you got a significantly more complex rocket than many others which fly with the difficulties of liquid oxygen. And will the launch trail be like the last year's, or will you have it be even bigger?
No, the launch rail will be the exact same. Maybe you saw last year our separate filling station that we used for the ground infrastructure that we have made some improvements to, just to make the workflow a bit easier, move storage compartments around, for example, improve weather sealing. But all in all, the ground infrastructure is, it's largely unchanged. Few improvements here and there, just for convenience for us and why we work on it.
TWR of the rocket would be similar, but you would have, of course, much more propellant to allow you to fly higher.
I have the exact person to talk to about this here. I'll just go get him real quick, or maybe I'll call him and we move on with the questions, and then he'll be here in like 2 minutes. Huh?
Have you started testing the engine already?
Not yet. We are just about to print the engine, and then testing should start soon.
The injector is probably the most complex part of the engine, so its design is very important to its functioning.
Yes, that's the biggest change that we made to the engine this year.
There comes our expert for the first to weight ratio. I'll give up my seat for him real quick. He can also tell you about our burn and in general the changes that needed to happen about the key performance data for the 9-kilometer launch.
Could you introduce yourself?
I'm Johannes. I'm doing the flight simulations and also the aerostructures stuff for Nixus.
The rocket this year will have larger propellant tanks than last year because you intend to fly to 9 kilometers. Will you have a similar TWR to last year?
Yeah, actually, the thrust weight will be a bit better at launch rate exit or when we start our rocket up because the thrust didn't change much or probably will increase a bit. And the weight actually got down from last year. So wet mass last year was around 105 kilograms. And this year it will be lower.
Well, what causes this change in mass? Is it because the rocket is a bit shorter?
That's part of it, but mainly we optimized every structural component, also our tanks a lot, and therefore we were able to increase the prime mass by a lot. For example, we have now forged carbon structural connectors instead of aluminum connectors. We do have a carbon fiber ethanol tank instead of an aluminum tank, which saves a lot of mass. And so on. We optimize basically every part of the rocket to save weight for this year.
How much weight do you avoid by using a carbon fiber tank instead of aluminum?
It's around 3 or 4 kilograms. We only have the ethanol tank as a carbon fiber tank because for the liquid oxygen, it's a bit too risky of the matrix material and the cryogenic temperatures, so it doesn't really work. Well, it might work, but we don't have the time till EuRoC to test it.
I'm going to start with the Pipe 5 for ethanol now, and then when we have the whole process tested out, then you will try to make top rack with different resin. This is then cryo-compatible, and then we will probably, of course, for the next year, then look into how we can make this tank also viable for LOX.
It's probably hard. Meaning it's either hard or it's expensive to use. To find and use a resin which is made for cryogenic temperatures. There are all polymers which tend to be quite fragile at those temperatures, as do most things.
There we have luckily the advantage that at the chair of a university, they have a machine to produce top rack, and they do various different tests for different resins. So there we could produce custom top rack for applications with the fibers that we want and the resin that would be cryo-compatible. So this is a potential source where we can then source such top rack.
You also have the problem that if the liner starts leaking somehow, then probably the resin would not resist very well the liquid oxygen.
We don't really have a liner. It's effectively a type 5 pressure vessel. So there's no separate plastic or aluminum liner inside that we went around. So the LOX would be from the start directly in contact with the carbon fiber.
And one can store liquid oxygen just without any liner?
That we have to see in the course over the next year if we can find a suitable resin that can hold up to this environment.
So regarding the airframe, it's all made in carbon fiber, apart from the Avionics bay, which is glass fiber. You chose to make it load bearing, avoid having reduced the number of structural parts.
Yeah, you reduce your number of structural parts, and also in the end you reduce your mass if you do it correctly.
And you increase the available volume that you have actually inside the rocket. If you would have an inside airframe and only an aero cover, then you'd have to make sure that all the lines can route around this internal structure. And now we basically just have a cylinder where we can then freely place components.
Assume that having a load-bearing airframe might be a bit harder to assemble once you are at EuRoC.
Yeah.
Yes.
It definitely is, but we make sure that we have our procedures aligned so we can still do that quite quickly because everybody knows what to do. We have it all written down. So we can fight this basically procedurally. And also, most of the segments we pre-assemble here in Germany and then bring it to EuRoC. And it's only the final assembly.
The airframe itself, do you buy a carbon fiber tube or do you wind it yourselves?
We wind it ourselves. At the chair of Composites, we have access to a winding machine where we do a lot of winding.
So we talk so we have our carbon fiber lead here as well.
Yeah.
If you want to talk more about the carbon fiber approach, we can get him into the interview too.
I do not wish to bother you all.
No, he's here already. So if you
have some structures talk.
What?
Hello.
Hello, could you introduce yourself?
Yes, hi. My name is Nelson, and I'm the fiber lead for this season. And I'm mainly responsible for our work that we do on composite materials that we mainly conduct the carbon composites, especially the winding of both our load-bearing skins as well as our Type 5 tank development, pressure vessel development. There we have access to a 5-axis winding machine.
So you wind your own airframe and tanks. You start with a spool of carbon fiber. Do you use like pre-impregnated fiber?
Yes. Until now, for winding, we've only used taupreg material, which is pre-impregnated, endless fibers, basically. Or to be more precise, it's we have spools of thin stripes that have a thickness of 5 millimeters, and no, they're 5 millimeters wide and 0.35 millimeters thick. And from the spool, they get pulled off, and then the machine drives around our winding tube or liner, depending if it's a tank or pressure vessel or a skin, and places the filament in its exact position as programmed in tools that we use for creating the G-code for the machine.
Is the nose cone separate from the rest of the airframe?
Yes. So for I don't know, is the focus on our upcoming vehicle or on the So for the upcoming, the nose cone is or will be the only component that will be made from a RF translucent material. So the only component that will be able to let radio waves through.
You'll use glass fiber instead.
Exactly. So we are not completely set on the exact manufacturing technique of the nose cone. So we will do it. We will laminate it from glass fiber, which would be more or less identical to the technique that we've used so far in our previous rockets. So it's an established manufacturing technique for us. But we're also trying to, we're investigating our possibility of potentially also winding it. So aramid taupreg material, so also same shape, general idea of taupreg. It's also taupreg, but aramid instead of carbon fiber.
Yeah, because the specific strength of aramid is higher than for glass fiber. So if you have basically it's not necessarily stronger than glass fiber, but it's lighter at the force it needs to withstand. So therefore, it might be better suited for a nose cone.
So aramid is more. It has a higher specific strength than glass fiber.
Yeah.
Is it more expensive?
Yes.
Compared to carbon fiber, where does it lie?
Between the strength of glass fiber it's between glass fiber and carbon fiber. So it's not as good as carbon fiber, but it's better than glass fiber, and it's radio transmitted.
And it should still be cheaper than carbon.
I mean, the problem is that it's not as widely used. More expensive, and in general hard.
Is there this much difference in specific strength that it's worth using it instead of glass fiber?
In the end, we probably don't necessarily buy our fibers. We try to get them sponsored. So for us, we want to build the most performing vehicle, and it would matter. But for example, if you were in industry, you of course would need to consider if the cost is worth the slight benefit. But we, as a student team, don't necessarily have that.
Also, the problem is that we're in general, we're interested in trying to wind the nose cone instead of hand laminating it, because it's technically a more secure and repeatable process to have it done by a 5-axis machine rather than by hand. And the problem with glass fiber is also that getting glass fiber taupreg is really, really hard, and it's barely used. In comparison, glass fiber aramid is more present in industry.
The tip of the nose cone will, as usual, be made of aluminum.
Actually, that's not quite set yet. For our solid project, we have now developed a Mark probe because that rocket flies to Mark 2.6. And yeah, so now for the X4C, we also wanted to use some sort of Mark probe or measuring device at the tip. And the material for that is, or it will be 3D printed, not 3D printed. And the material very much depends on where we will get space on a print bed on a metal 3D printer. So it may be anything from aluminum, titanium, or to Inconel. It's still very much out there.
What is the expected top speed for this new rocket?
Around Mach 1.2.
You have interest in measuring the speed?
Yeah, basically measuring the speed because yeah, it's a nice scientific thing we can do. It's nothing that we require, but we of course want to do our small projects and have fun while doing it. So yeah.
Are other structural parts made of composites apart from the airframe?
The engine mount is 3D printed, but I don't know. It's not a composite, right?
Yes, absolutely. There are. Until now, for connecting our segments, we usually use aluminum milled ring connectors, which we're now getting rid of in favor of block connectors that are made from forged carbon, so basically wet pressed. So we put fiber snippets in a mold and add resin, and then press it to get to condense it and press out excess resin. And yeah, we use those for connecting our segments. So they're also a major structural component, which is now made out of composites.
Yeah, also as already discussed, the ethanol tanks also come fiber. And then we also have in the recovery segment the bucket where the recovery parachute has its housing, basically, is also made from carbon fiber.
So you're also investigating this new manufacturing, pressed composites?
Yes. So it's not entirely new. We used it also last year for leading and trailing edges of the fin can, which we now did again for the solid rocket project. It's not entirely new, but in a major structural function, it's new.
In terms of mechanical properties, where does this, I assume it would be weaker than wound carbon fiber?
Yeah, theoretically, if you were to produce a plate, it would be less strong. However, the component we have, for example, the structural connector, you can't really wind that or make it out of head laminated. So and also it majorly depends on how you produce it. So it's very manufacturing process dependent, which strength you get from it. So you want to use basically long fibers or the longest fibers as possible and lay them in your part so they can transfer the loads best, versus very small fibers that just help it a bit but don't increase the strength by that much. It's basically the same for 3D printing. You might know that there are continuous fiber 3D printers, plastic 3D printers, where the material is then a lot stronger than the chopped up carbon fibers, basically in the 3D printed filament you can just buy at your store. Yeah.
I see that you are planning to make a lot of improvements, let's say, to reduce the weight, to optimize the structure of the rocket, to reduce the weight. Is this important from a flight perspective, or are you doing it only to experiment with more complex, with the new things?
It's a bit of both. So first of all, the reducing the mass is of course important for the flight performance. It heavily depends on your dry mass. And then the second thing is, of course, we want to experiment and find out about the best technology.
How long does it typically take you to wind the airframe of the rocket?
Winding itself is negligible. What takes time is every step you need to take to get to the machine moving the way you want to. Yeah, I mean, from initial data acquisition, like where do people want holes, which is a headache, over then simulating and trying to find out what layup we need. So first of all, what angles we want to wind at, what is optimal, how many layers, and then also like a major step we're now going towards is local reinforcement, because we want to really optimize this layup. So for example, wherever they may be rivets, we need to locally reinforce it. If we're now arriving at thicknesses of a millimeter, and after we've figured all of that out and we have our layups, we need to then generate our winding codes, make it possible that the machine can actually do it, because of course, fiber slip is a big problem if you're really winding around a circular end section at like very, very flat angles. Setting all of that up, we're now using new and more sophisticated software for operating the machine, which we're initiating ourselves, so without the support of the chair. So we're basically doing all the work of getting all the machine parameters into this code, which is an insane amount of work. Test driving those codes, reiterating, of course, getting the winding tubes done the way we need them. Then the mounting setup, which is also not to be underestimated. That everything is very rigid as we wind with a non-negligible pre-tension in the fibers. So it needs to be really strong. And also the tubes we have are pretty heavy, as well as the bosses that come on the ends. All of that, plus then, getting everything set up. And then really the actual winding of the fiber is like the last 5% of the time, and I would say it's 2% of the effort.
Yes, of course, you have the machine that does the winding, and the complicated job on your part is to program the machine to do what you wish it to do. Since it's not a homogeneous material, but you have a fiber that is wrapped, you have to also make lots of considerations from how the final part will be mechanically depending on how you wind it. Composites are certainly hard in this sense that you have the carbon fiber, which is strong, held in a resin, which is of course much weaker, so it is only strong in the direction that you wound it in. No, I was just seeing some of the difficulties.
We agree.
Yes, we agree.
It is certainly an interesting part of the rocket making process, and a very important one, of course. Have you changed much since last year? Do you plan to change much from last year in the airframe?
Last year we had 5-layer skins all over the rocket. So the layup was more or less identical over all segments. And we're now trying to individualize trying to see where we actually need how much, basically, and not everywhere the same. And using the worst case layup for the entire rocket. So, which is also heavily needed because we now have the recovery, the sideways recovery system, which requires a rather large hole in the otherwise load-bearing airframe. Of course, we cannot make every segment as thick as that segment. We're diving heavily into, as I said, finding out where we need what thickness, what layup, what angles, and of course, what local reinforcements. And basically, we don't have the final layups yet. as I said, that depends heavily on all the holes that we will have in different positions. But as it looks right now, the recovery segment will be in the ballpark of 6 layers or something. That's how much we had for the solid rocket sideways system. So somewhere in that regime, plus reinforcements or more. And otherwise we're pushing for 3-layer skins and the other interstages. Plus, of course, the reinforcements. But as I said, that is still not finalized, and we're still very much in the design loop process.
Do you have some specific simulation software for seeing what thickness is needed of the hull?
I mean, yeah, of course, that's the main part of that design process, that design loop. Everything regarding this topic solely depends on the simulations that we do. As I said, like this now so heavily depends on all the holes and cutouts and where they are and how large they are, that it does not make sense to do them if we know that the holes and cutouts are still very much up to change, or even when their existence is not set. I mean, of course, if a hole is there or there or there, does not matter that much, but their existence has to be, I don't know, announced, and that is just very unrealistic if the entire system is not fully defined or fully reviewed, or in general, I mean, this weekend was meant to clear all those topics, so to get to figure out what holes we will need in the rocket. It just did not make sense to add them in any rocket CADs, only for them to be moved around 100 times after. The main simulation part of the development will start Monday morning after this weekend, once all the holes are set. That's where we're at right now. It just did not make sense to start before. For the recovery segment, as that hole is already set, the large sideways hole, the hole was already set, the size and the position, so we already have a simulation for that segment.
Yeah, so you have decided to change noticeably your recovery system from last year. You will have the parachutes ejected sideways.
I could talk about it, but I'm not qualified enough. So I'll hand back over.
So for the recovery system, one big thing for us this year was to try to move away from the CO2 system that we used to have to eject the nose cone. This is because you needed black powder, and from a Europe perspective, black powder adds risk to our integration because it takes a lot of time to wheel the rocket over to the pilot tent and handle the black powder together with an official. Also it makes it difficult for us because getting black powder is not that easy in general. So the simpler and less overhead we have there, the better. And that's why we want to move to sideways ejection. We've already tested it with our other project, the solid project that Nelson already mentioned. And there you can just simply cut a rope instead of having to generate gas. So that's much simpler.
Wait, so the parachute will be ejected sideways from the rocket?
Yeah, exactly. So we used to have a parachute packed in the nose cone, and then the nose cone would be ejected at the highest point in the flight, and the parachute would be allowed to unfold because the nose cone is not on, right? And this year what we want to do instead is to have a hatch on the side of the rocket, pretty far up, right? So right below the nose cone, basically. And at the highest point of the flight, this hatch will open, and it will release the parachute through the side of the rocket. And then, if you imagine this is the rocket, then it will dangle, so like this, right? And the idea is that to get this hatch open and the parachute out of the rocket, all you have to do is cut a rope, and this rope holds the hatch in place. And that is much simpler because, in one sentence, it's easier to cut a rope than to eject.
So you will have a spring that pushes the parachute?
There's also springs on the hatch, for sure. It's more of a backup system. We've noticed that packing the parachute very tightly, which you want to do anyway, to optimize the volume, the force from this packing will already induce enough tension on the hatch that it will eject by itself, and then there's springs as a secondary measure.
Having the parachute be on the side of the rocket surely increases noticeably more stresses on the airframe itself, I would assume.
To a certain degree, yes. Well, not exactly more stresses. It's really different because the attachment point is in a different spot, right? So on the one hand, having an off-center attachment point introduces a bending moment that you wouldn't have, or like a bending axis that you wouldn't have before, right? But since the ejection is closer to the center of gravity, your what do you call it in English? Your lever arm is much shorter, right? So the recovery shock is much less severe.
So you have lower peak force. So
we expect to have lower peak forces. Yeah.
In the end, it will be better for the airframe.
We hope so, yeah. I mean, it helps us to reduce structural mass as well. So just from that, we already get less forces. And then again, the lever arm.
How wide will the rocket in terms of diameter?
We stick with the 200 millimeters outer diameter.
So you have quite a bit of space to do this sideways hatch.
Well, I mean, it's relative, right?
Yes.
It depends on the dry weight of the rocket, which we were able to reduce. So that way you have a smaller parachute as well. But still, how to put this? You still need sort of a big hole to eject, right? So it's about space on the one hand, yeah. But the new challenge sort of that we introduced to the system with this change is that the ejection needs to have a huge hole in the side of the load-bearing structure. And that sort of has to be taken into account when designing the airframe. So the space is all right, I would say. You can simply create more space by elongating the segment. But the trouble is that you also increase the hole size there, and that's really what limits you.
Will the drogue and the main parachute be shot out of separate hatches?
No, there's an argument to be made in favor of it, yes, but if you can reduce the number of, let's say, ejection events, then you also reduce the points of failures. We are also developing a reefing system. The question is if it will be ready in time. I think there's a very good chance that it will be. So that way you would have two deployment events, but on the same parachute, right? So that would even negate the necessity for a second hatch. And starting from this thought, we designed the drogue main system in a way that it also comes out of the same hatch, so that it's all compatible with the reef system as well. That's sort of the idea. And then we still have backwards compatibility, and we can switch the recovery systems until the day of the launch. Last year there was a lot of changes and adaptation because of the weather to the recovery system. So having this flexibility will allow us to live with this last-minute kind of change.
Have you made other changes from last year to the rocket?
Well, one change that we only touched on briefly so far, I would say, is the EuRoC. That one's really key, one of the key developments for L9 for us, right? Because the mechanical regulators that we had found so far were always super heavy, not exactly rated for the flow that we would like to see, and had a huge droop throughout the burn, right? Maybe Moritz can talk more about the implications of that, but it will be super interesting to see how they perform in flight. In testing, they've already been very promising, I would say. So these EuRoCs allow us to have a much more accurate set point on the pressure in the tank, and then hold it much more accurately than the mechanical regulators can. And what that means, Moritz can tell us.
Yeah, the first problem, if we start from the beginning of the burn, was that the regulators were always, say, a bit undersized for the flow that we needed, because otherwise it would be just way too big and heavy. And that meant that we had to basically artificially set the set point a bit higher than what we actually wanted, so that once flow stabilized, we would land at the nominal value that we targeted. But this also means that at the very beginning of the burn, we have a lot higher flow, which is not that desirable, because that would then cause an RF shift. And because with our startup, we open the ethanol first to make sure the engine is cooled when we have ignition, which then means that the liquid oxygen main valve would open after that. And then the ethanol would have already set it at a nominal pressure, while LOX opened at a slightly higher pressure, which would then cause an RF shift towards a hotter load point, which is undesirable for the lifetime of the engine. And then both of the pressures would slightly droop down over time, which then also causes, again, an RF shift and thrust shift. And with the EuRoCs, we can much precisely set the load point. And theoretically, we can also change the load point during the burn. And we don't have the problem of having to basically artificially set different pressures what you actually want, and the propellant flow should be much more desirable, especially when opening the main bus.
These electronic regulators work by having like a valve whose opening is decided by a pressure sensor.
Yeah, pretty much. We've already seen some other teams at EuRoC use those for propellant valves, or like a similar concept, let's say. For that, we wanted to stick with our solenoid valves. We like the safety concept of it. But for the regulation valves, we've now decided to get more competition streamlined, let's say, because in testing, mass doesn't matter, right? But the flight bus, so the concept is that you have a off-the-shelf ball valve, and you attach a servo motor to it, and then the PID loop decides on the opening position of the ball valve using a pressure sensor on the propellant tank.
How does it compare to a mechanical pressure regulator? Is it more precise? Is it a bit slower to compensate? How?
Like Moritz already pointed out, right? It's much more precise, and it's faster to keep up with the flow. And the nice thing is that it's not set in stone, because again, it's a PID loop, so you can adjust the parameters, and then you can make it more aggressive. You can make it smoother but slower. There's a trade-off there that you can make. So this is a freedom.
This way, you would also be able to like throttle during flight.
Yes.
Yep.
This is exactly a very interesting topic that you mentioned. We looked also into that. The main issue why we are not doing it this year is that with our current injector design, the Impinger, we can't throttle down far enough where the vehicle would be sufficiently slow to not to significantly reduce the aerodynamic losses that we experience. We can throttle roughly to 80%. This is where we set like our limit to ourselves that we want to do with this injector. And then we did an extensive optimization study to see if we throttled at which point, how far, what that would have an effect on the flight. But yeah, as I said, the result was that we can't throttle sufficiently far enough for it to make sense. Plus, we are limited in the size of the propellant tanks that we can manufacture, because at some point, if they just increase in length, it's increasingly hard to find machines where you can actually manufacture them on. So those were two main constraints that then led us to not do that in flight. We'll probably experiment with that on the ground. We can do that just when we have time for that to gain a bit of experience in that, collect some data, but we will not be throttling in flight this year.
But we do have engine development coming up that is much more throttleable. If you want to use these last 2-3 minutes, we have our engineer here who works on that engine. We could get him inside real quick in the call.
Well, if in 2 minutes you must go, then it's probably best suggest to. And thank you for coming. It's been an interesting conversation we've had. I hope I can see you at EuRoC this year.
We hope so too, Etto. Thank you very much for inviting us for this interview. I mean, I had a great time too. How about you, Moritz?
Yeah, same.
Perfect. Yeah, we'd love to do it again, and we'd love to see you at EuRoC again this year. And yeah, thank you. See you around.
Bye.
Bye-bye.